This is video 7 of Unit 1, and in this video and the next we will begin talking about electron orbits, or the specific behavior of electrons around an atom. Don't be concerned, the nucleus here is definitely oversized. The nucleus, remember, is really tiny. The electrons make up most of the volume of the atom, so that's why we study electrons in detail, because they are what makes up most of the atom's volume. So we'll begin by discussing Mr. Einstein, Mr. Albert Einstein, who performed some interesting experiments and made a contribution to our understanding of electrons. He performed what's called the photoelectric effect. Now here it says electrons can get released when light shines on a metal. So if you shine light on a metal, electrons, because all matter is composed of electrons and protons and neutrons. The electrons, though, being on the outside, can get ejected. Now, what it looked like was something like this. The light had to be at a certain frequency. A threshold frequency means it has to reach a certain frequency before the electrons were ejected. So, an example of this, red light could not eject the electrons, but anything above green light could eject the electrons. Now, this is metal potassium, and it takes 2 electron volts to eject an electron. And the electron is around the nucleus, orbiting around the nucleus at a certain energy. And to dislodge it, you have to give it enough energy to kick the electron off, because the nucleus is actually pulling the electron in with a certain force, you can say. Now, red light, if you calculate, red light has an energy of about 1.77 electron volts. Each little photon of red light has that much energy, which is not enough to eject potassium's electrons. But green light, having 2.25, is enough. And anything above green light, blue light, definitely has enough energy to eject electrons. So this idea had proposed to Einstein and others that these electrons that orbit the nucleus have a certain energy, and unless you reach that energy, you will not be able to dislodge, to eject the electron, which led to our understanding of orbits. So electrons exist in certain energy orbits. Now we have orbits in quotation marks because, as you'll see, this idea is not the same as we initially thought. Initially, scientists thought that these orbits are clean orbits, like planets around the sun, for example, which will not be the case. As we'll see, this will not be the true picture. But it allowed us to see that there are certain energy levels, certain energy states that the electrons have to occupy, which is correct, is a correct understanding. And solar panels, today's technologies, are built on this principle. So light from the sun hits this material, special type of material, and then electrons are ejected. As electrons are ejected, they're actually captured then, and this can allow us to form some electricity. You can harness electricity just from the sun. So light has quite a bit of energy that can be used. Next, we're going to talk about the emission spectra of different elements, and this will be kind of the core experimental finding that allows us to see electrons on the inside. Remember that the reason we're studying light is because light allows us to understand how electrons behave. You may be aware of this phenomenon. It's called the northern lights. Fancy word is aurora borealis. And this can be seen in northern latitudes because of high energy electrons hitting the atmosphere, or high energy protons actually from the sun, hitting the atmosphere, ejecting electrons, and producing light. So light is directly connected to electrons. By studying light, we can see electrons. So on Earth, what we did is we took a gaseous element and then heated the gaseous element until it glowed. Now, as it glowed, that means it released its light. And as it releases light, we separate that light into what's called a spectrum, which is simply a broken up, pass it through a prism, for example, and you can break the light up into its individual wavelengths. And what you see is you see a spectrum with a bunch of lines, tiny, tiny lines, thin lines spread over the entire visible spectrum. And the question is, how are these lines produced? There's a lot of them, and they are related to the electrons, somehow to the electrons inside of these atoms. And this is really the key to understanding how light and electrons are connected. So the story goes something like this. When an electron absorbs a quantum, which is a specific amount of energy, it will move farther from the nucleus. Because remember that electrons which are closer to the nucleus will have less energy. Electrons further from the nucleus will have more energy. So here we have two electrons. This one has more energy, this one has less energy. So the electron jumps higher up. And this is called an excited state. The electron is not excited. Now, it won't last long in this excited state. The excited state, electron falls back down and emits a photon of radiation, and it falls back down to its ground state. Ground state means where it began originally. So from this you can see that a photon of light is released. Now, really important, the statement at the end, the frequency of the photon corresponds to the energy difference between the states. So the electron jumped from here to here, and this energy difference matches exactly the frequency of this photon. Remember, the frequency of the photon, you can use the equations E equals hv to get energy and frequency from frequency and vice versa. So those two are connected. So that allows us to see the frequency, and then the frequency is actually related to wavelength, which means the color of the light. So because we can see light's color, we can then infer the energy inside, energy levels inside of an atom. And this was the central concept. So for example, if you take a look at hydrogen, if you heat up hydrogen and you split hydrogen up into its spectrum, what you'll see, first of all, hydrogen comes out as a magenta, kind of purplish light to your eyes. But if you split that up, you'll see four. Here we're not showing the green one for some reason. There should be a green line as well here, like so. There should be 4 lines that you see in the spectrum, and these 4 lines correspond to the energy levels inside the hydrogen atom. So in fact, the hydrogen atom has 4 energy levels, 1, 2, 3, and 4, and they're actually sort of bunched up like that to match up the spectrum that you see. And these 4 energy levels, an atom actually has an infinite number of energy levels. They just keep going up. But these 4 are 4 transitions that the hydrogen undergoes. So these aren't represented exact energy levels, but these are the 4 transitions that the electrons can actually jump between. And we'll see this in a little more detail. Here actually is the true rendition of hydrogen's electron levels. So hydrogen here has an infinite number, we'll say, of energy levels, but there are 4 jumps that we can see. Now, a lot of the jumps we can't see. If the electron jumps from energy level 2 to energy level 1, it releases a type of light that's in the UV spectrum, which we can't see. If it jumps from 3 to 1, or from 4 to 5, from 6, or from anything else down to 1, the energy level difference is big enough to correspond to ultraviolet light that we can't see visually, but we can detect it, obviously. But then comes, this is called the Lyman series. Then comes the Balmer series of lines. This is the important one, because this is the one that we can actually see, or 4 of these we can see. So anytime an electron transitions between 3 and 2, 4 and 2, 5 and 2, or 6 and 2, each of these is visible to us. The difference in energy level corresponds to the visible spectrum, if you calculate its wavelength. So these really are important, and this is what we visually will be able to see, and we'll show it to you in class as well. There are a bunch of other transitions that are in the infrared region. These are, notice, small transitions, small enough to where we can't see them, and so we can detect them with special instruments. But every element can actually produce a lot of lines due to the fact that the electrons are jumping between these different energy levels. Now, we can calculate the electron energy in a simple atom. Here it says a simple atom, meaning only 1 electron, using what's called the Balmer's equation. And here, the Balmer's equation says that the energy of the electron is calculated by multiplying this constant. This is called the Rydberg constant, by z squared over n squared. Now, z is our atomic number, which is the number of protons. and then N is used to designate the energy level. So at level 1, level 2, level 3, level 4, level 5, and so on. Notice that I think in your notes I've got a negative here. Go ahead and use the positive. That way we'll just calculate how much energy the electron has. Now, units of the energy, as before, will be joules. That's because the Rydberg constant is actually given in joules. So we'll go ahead and use this to calculate how much energy each of these has. What you could do then is compare that against another energy level's electrons and subtract them, and you'll see or be able to find what's called the change in energy. This little letter here is delta, which means the change in energy. And essentially that equation, Balmer's equation, was combined together to create this Rydberg equation that allows you to see how much energy would be released if an electron actually jumps, because the previous equation just tells you how much energy if it sits there. But now we're going to calculate how much energy if it jumps between the two different levels. And this again is the constant that we saw, which is 2.18 times 10 to the negative 18 joules. And then here we've got 1 over n squared F, which refers to the final energy level, and then minus 1 over n squared I, which means initial level. So say if the electron is jumping from level 4 to level 6, it jumps up. This is the final level, this is the initial level. So you just actually put 4 in here, square that, 6 in here, square that, and calculate it, and you'll actually get how much energy the electron releases or absorbs. Now here it says this equation really only applies to the hydrogen atom. That's because the hydrogen atom is really the only natural atom that has one electron. It turns out, as you'll see, that electrons are really complex. And if you put two electrons together, they begin behaving more like a wave, and things can get crazy after that. So this equation we'll use just to prove hydrogen's spectrum, but beyond this, we're not going to be able to use it. To go beyond hydrogen, we'll have to consult this guy, Mr. Schrodinger, Edwin Schrodinger, and he gave us some interesting equations. So here it says for higher atoms than hydrogen, electrons affect each other, and we have to use wave-like equations, and Schrodinger provided these wave-like equations. So make sure you memorize these equations. That's actually a joke. No worries, these equations are far beyond us. These are involving higher level calculus, and nobody really much uses them in chemistry unless you're doing theoretical physics or theoretical calculations. But the electrons are really complex. So from here on out, what we'll do is, well, before we go on to tell you what we do, there's a guy by the name of Heisenberg, Werner Heisenberg, another dead guy with a fine picture, and he showed a lot of these guys talked about the strangeness of electrons and their behavior and the wave nature of light and so forth. And he showed what's called the uncertainty principle, which is a really strange principle, hard to understand, and made us think that matter is really strange. And here he said that the more precisely the momentum of a particle is known, the less precisely its position is known. And there's an equation for this. We're not going to use this equation, but this here is the position of an electron or particle, and this is the momentum of the particle. So where it is and how fast it's going are the two things we're measuring. And this has to be greater than or equal to a certain constant. This is actually Planck's constant again. And what this is saying is the better we know the position where the electron is, the less we know how fast it's going, how much energy it has, and vice versa. If we know how fast an electron is going, then we don't really know where it is. So there's actually a physical limit to our knowledge about the electron's position. And it's not that our instruments aren't good enough. This is a principle of science. This is because we're looking at an atom, really, really tiny scale, but the laws that govern the atoms and electrons' behavior are actually different than the laws at our level. So there's a physical limit to our knowledge. This is called the uncertainty principle. So, that being said, what we'll do from here on out is we will treat electrons less mathematically and more conceptually. We'll talk about them and where they are and their configuration and so forth. And because each element has a different arrangement of these electrons, every single element has a different number of electrons and arrangement with unique energy states, and especially when the electrons combine their waves, they have unique energy states. Every element gives off a unique spectrum. So here are two different elements. Now to your eye, if you were to see these two elements, they'd probably look pretty similar, maybe one slightly lighter than the other. But if you break their light up, you will see that they have unique energy levels, and there are a lot of lines in these energy levels. The electrons are interacting in a specific way, but in a very complex way. So for example, if you heat up nitrogen and look at its light versus argon and look at its light, you'll see that to the visual eye, both of them look roughly pinkish purplish, but if you break up their spectrum, you'll see that they have different spectrums. Nitrogen has a lot of yellow, whereas argon has less yellow and more purple. So we'll study this in much more detail. An interesting historical fact is that elements were actually discovered on this principle. A famous element that was discovered this way was the element helium. The word helium actually means sun. Helios is Greek for sun, and from the word heliocentric. You may have heard of that word. And helium was discovered in the sun before it was discovered on Earth. And the way they did it is they took helium's spectrum, or they essentially studied the sun's spectrum, and they found essentially a signature of an element that they did not recognize, and they theorized that there must be an element on the sun that is not on the Earth. Eventually they found it on the Earth. There's plenty of helium here on Earth, but it was first discovered on the sun. And by the way, there's a difference between what's called an absorption spectrum and what's called an emission spectrum. So an emission spectrum is when you heat up an element and it gives off light. The scientists actually took a look at the absorption spectrum of the sun, for example. And what the sun did is the sun absorbed this light before it reached the Earth. And by seeing dark lines, we saw where the electron levels were, essentially just kind of backwards. But both of them give you the same information, just kind of backwards. All right, so this concludes for us this lesson of Unit 1.